let's make sure. I'll fix it right now.
Okay, the simplest circuit you can make, of course, is a single transistor. And if you tie the gate back to the drain back to the gate, then you get a diode connected transistor, right? And this circuit you can tie to ground or some other voltage. So it depends on where you put it in the circuit. And so this circuit of single transistor circuit over here, it's if you tie the gate back to the drain, it guarantees that this transistor is in saturation, right? And so if you want to write the current through this transistor as a function of, say, VG, then in subthreshold, that's going to be ID equals to I naught E capital VG minus VS. So this would be VS. And if your VS is ground, then it makes it very simple. So basically, it's just I naught. So this would be I naught E capital VG, right?
Could I ask a question here? Sorry.
Sorry?
Could I ask a question here? Sorry.
I don't think I understand what you're saying.
Sorry, I just wanted to ask a question here, and from last lecture, why in these equations you're able to ignore VT most of the time?
Oh, this is subthreshold, a subthreshold equation.
No, it's in dimensionless units, right? Units of UT.
Oh, you're talking about UT.
Yeah, UT.
Is that what you mean?
Yeah.
Okay, that's what you mean. Okay, I thought you meant VT. Yeah, so it is there, but it's not being ignored. So if I happen not to write it, it just means that it's just in terms of units of UT. Yeah.
Okay, the current itself is in units of UT.
The current?
The current, no, this part here, the exponential.
Oh,
Yes.
okay.
Voltage. That's a voltage.
Yeah, so
Okay.
it's
Current is in
it's
amps.
voltage over voltage.
No, yeah, I meant, okay, thank you.
Yeah, right, so it should be unitless. And then this gives you the units of current. Okay, and so this, the transistor operating saturation, this is going to be true whether you're in subthreshold or above threshold. And so again, it's useful to know that you have these two regions of operation of the transistor, the subthreshold, right, where the gate voltage is less than the threshold, and then the other region when the gate is above the threshold, right? And so that's the above threshold regime. But in both regimes, right, you have the linear and saturation region, right? And so there, what you look at is the current as a function of the drain voltage, right? And so if you do this for subthreshold, then you get some increasing current with VD, and then at some point you saturate, right? And so this is usually around 100 millivolts, okay? And this saturation, as you can see, there's a slope to this curve, right? And so the slope of this curve is GD. So this is the drain conductance. And so depending on the size of the drain conductance, so if this slope is very low, then you can see it goes backwards, and then you get this early voltage, right? And so depending on the sizing of transistor, then you're going to get a higher or lower early voltage, depending on the slope.
You should ask a question, Chi-Chi. How can I make that VE bigger? Yeah, so anybody want to say how, you know, if I'm free to draw the transistor, how can I make the VE bigger? Does anybody know?
Doesn't it depend on the length?
Exactly, proportional to the length almost. Right, why is that though? Why is it kind of proportional to the length?
I thought that because, and maybe I'm wrong, but the gate is like a resistor that's long, and like this causes that resistance as it gets longer.
No, that's not it. Remember how there's a region around the drain end that's the depletion region? Maybe Shichi can draw it right around the drain. You can just circle it there. Right around the drain end of that transistor, there's a depletion region, right? And that's fixed size. So if you make the transistor longer, that depletion region as a fraction of the whole length becomes smaller and smaller. So the effect of that change on the length, on the overall length of the transistor, if you make the transistor really long, then that little change in the depletion region width is going to get smaller and smaller as you make the transistor longer. Oh yeah, this is great. Somebody else can draw at the same time, right? Is it clear now? The longer you make the transistor, the smaller the effect of this little change. Maybe Shichi can draw the change. if you make the drain voltage higher, the depletion region around the drain gets wider or narrower? To make the drain voltage higher. Who says wider? Nobody? Nobody says wider? You say yes if it's wider, or no if it's get narrower.
It's in the chat, Toby. Typing in the chat.
Oh, in the chat, I see. You guys know you can also say yes, no. That's good. Yeah, you guys can speak up. Yeah, wider. Okay, that's correct. Yeah, so if I make the drain voltage higher, the drain depletion region gets wider, and so the channel gets shorter. And so the channel gets shorter, either the diffusion current gets bigger because, you know, the gradient of density is higher, or if you're above threshold, why does the current increase as you make it shorter? It's because you have a bigger electric field, right? A shorter, you have the same voltage, but you have a bigger electric field. So a bigger electric field along the channel, you know, same voltage, but shorter distance, bigger electric field means more drift current for the same charge density. Yeah, anyway, sorry to interrupt. That's the whole channel modulation stuff. So basically, if you want a flat curve, make a long transistor. Simple. Okay.
Okay, so this thing about the early voltage comes into play when you now take this single transistor and now you make a current mirror. So it's good to have that discussion. So now I can take this and then I could connect this now yet to another transistor, right? And let me just delete this for the moment. And so you guys know the circuit. We went over the circuit last week. So this would be your input current, and this would be your output current. Okay. And so let's assume this is I1 and I2, corresponding to transistors M1 and M2. Well, actually, I shouldn't. Let me not use this. This is just I out. Let's just do that. Okay, then because the gate voltage is the same for both transistors and also the source is the same, so now the only thing that's different is the drain voltage of this transistor versus this one. But you can guarantee that this transistor is in saturation, then what you can write is I out equals to, again, I naught kappa VG over UT for this transistor, and for I in. Right.
By the way, Shuchi, you might say this transistor, but we don't see your mouse pointer. So if you want to, you know, when you say this, you're pointing with your mouse, but we don't see the mouse pointer. Do you guys see the mouse pointer? I don't. Can you move the mouse around there? Yeah, there's no mouse pointer.
Oh, all right.
Yeah.
So what you can do is I would just circle it.
Yeah.
So this is when this transistor, I mean, okay, since I've given the name, so it's M2, right? So if I write the current through M2, then if you assume it's in saturation, then you get this equation. If I now look at the current through M1, then you get this equation, and you can see it looks similar, or actually looks exactly the same. So in the ideal situation, I out equals to I in.
Yeah.
All right. But
I'm not sure why. Yeah, you're sharing the screen, but I think you're just sharing the window or something. That's why we don't see the mouse pointer. Did you really share the whiteboard screen? The whole screen? Because if you stop sharing and just share the entire screen, then you should see the mouse pointer too. Now I saw it for a second. Now I see the mouse pointer. Oh, yeah. Maybe if you put the mouse there, and now if you use the pen, it moves the mouse around. Yeah, now move the pen around.
I cannot move the pen around.
No, I mean, take the pen on this. Yeah, now we see it.
I'm not sure what you mean.
No, put the mouse back in the page. Put a mouse back inside. Now just take the pen and move around.
Nothing happens.
The mouse doesn't move?
No.
Now it moved.
No, that was me moving the mouse.
Yeah, I don't know why. Somehow you can't see the stupid pointer from the mouse. The pen doesn't move around. Sorry about that. I'm trying to figure that out.
Yes. Okay, so that means that in ideal cases, I out equals to I in. And as we discussed before, the drain voltage can affect the current flowing through the transistor itself, right? So that means I out is not really I in, right? So here, so I out is actually approximately I in, because it's going to depend on where this drain voltage sits. Okay, so now the two ways of making the gain of the trend, or changing the gain of the current mirror. So this is a, if you like, an NFET current mirror circuit.
Well, just ask them
So
what's the
if I-
simplest way. What's the simplest way, right? To change
Yeah,
the
they
gain.
learned that last week, so
Yeah.
I'll ask in a second. So let's assume now that I want to make I out equals to A times I in, and A has to be greater than 1. So last week you learned 2 different ways of doing this. So can someone, yeah. add
Somebody
multiple-
already wrote it on the chat. Yeah.
Yes, that's right, Adrian. But which side do you add it on? Do you add it on the input side or the output side? On the output side. Yeah. So basically you want to do it here.
It's just more copies, right?
Right.
Yeah.
Okay. I M2 equals to AM1. Yes. Okay, you can do that too. So basically Sham's saying that you can also change the W over L of this one transistor. Right. So instead of
What's
making
this? M2, you mean?
instead of, yeah, Toby, don't worry. Can I?
Yeah.
So if we say that M1 has a width and length of W1 and L1, and M2 has a width and length of W2, L2, aspect ratio, then you can make W2, for example, W2 is 8 times bigger than W1, right? Or correspondingly, you can also change the length of the transistor. Or you make multiple copies. So basically, W2 equals to L2 is W1 over L1, and you make multiple copies. Yeah, all are possible. Okay, now the other way of doing it, can someone say? What else can you do? Especially if you want to be able to change it after the chip comes back. Right.
Well, it's already written on the chat, right? Different source voltage.
So that means that now you have VS1 and VS2, right? So M1 and M2, and again now, it's capital VG minus VS1 over UT and capital VG minus VS2 over UT. And then what you can do is compute I out over I in, and that will give you E kappa, sorry,
Oh,
it's not
kappa.
kappa. It is actually VS2 minus VS1 over UT. Okay. So which means that if you want A to be greater than 1, then VS2 has to be greater than VS1. So again, in this case, what you do is usually you want to have not so many bias voltages. So you set this to ground, and then you would change VS2, right, for the gain that you're looking for. Okay, all right. So now the next thing that we can do, if you remember, is that we have a source follower circuit. So let me just make a, okay. So this is the input, this is the output, this is the bias voltage, IB, and this is the what we call an NFET source follower. I can do the equivalent PFET source follower. And remember, you know, any circuit that you come up with, you can always make the complementary type. And what you do then is you take the circuit, right? And then you flip it over, right? You change it to PFETs and you flip the whole thing over, right? And if you do this, then what you get now is this VD. This is now your VD, right? This is V in, and this is V out. Okay, so you guys get that? Just type yes in the chat if you do. Okay, so you can do this for any circuit that you come up with, and you see also with the transconductance amplifier, you can also flip the whole thing around, right? So the difference between this circuit and this circuit is that you have a current sink over here, and you have a current source over here, right? But they're both followers. And you see that one of them actually the output in this case, this output is lower than the input. And in this case, the output is higher than the input. All right. So let's just stick with one of them only for the moment. So we're just going to stay with the NFET. Okay. So now the way that you can solve for how V out depends on V in is by using Kirchhoff's current law, right? So you know the current through this transistor M1, so let's call it I1, has to be equals to IB, right? So in steady state, there should be net zero current going into this node. So what you get then is I1 equals to IB, okay? And then you can write the equation for I1. So that would be I naught E capital V in minus V out. Again, we're going to assume that these transistors are all operating in saturation. Okay. And then you can write it for IB, and IB is going to be I naught E capital VB. And then the VS here is ground, so I'm going to drop it. Okay, now you can then solve for V out. So what you can see is IV in. So just basically you can cancel I naught, and then you just look at the exponents of the exponential. So you get capital V in equals to minus V out equals to capital VB. And so that means that V out equals to capital V in minus VB. Okay. So what you can see here is that the output is always lower than the input by the bias voltage that you place on this bottom transistor. So it's a follower, and the output comes from the source of the top transistor. Okay, so now, so that's the source followers. The next thing is the transconductance amplifier. And so actually, this is what we are going to go into more detail today. So first we start with the diff pair, the differential pair. And so we're going to have VB, we're going to have VS. This is the what we call the common source voltage. This is V1 and V2. And the current flowing through these transistors are through transistors M1 and M2 are correspondingly I1 and I2. Okay, so now again we use Kirchhoff's current law, which says that I1 plus I2 is equals to IB, right? So we're applying the KCL at this node. Okay, and again we're assuming saturation for everybody. Right, so which means it's easier to solve the equation. So what we get is I1 equals to I naught E capital V1 minus Vs, I2 equals to I naught E capital V2 minus Vs, IB is I naught E capital VB. And so then you have to solve for Vs because that's the only thing that you're not driving, right? Basically, you're setting V1 between VB. And so let me just, I derived this last time. We can go through it, or I can just directly write out the equation, or I derive it. Okay, hold on a sec. So could you guys derive it last time? Okay, so Nicholas. There is a question from you guys. Can we assume that they have the same kappa and I naught in general? Yeah, when you're analyzing the circuit, yes, you can. Right, but of course, you know, okay, there's this thing of transistor mismatch that we're not talking about here, but usually when you fabricate a transistor, even if you draw them exactly the same, they're going to have some difference in the current that flows to a transistor. But when you're doing this kind of analysis and understanding the circuit, you can assume they have the same kappa and I naught if you have the same gate voltage, okay? Because kappa changes with the gate voltage. So for the case of the current mirror, yes, you can assume that they're the same. Any more specific requirements? Well, the drain voltage of the output transistor can affect your output current. Nicholas, what are you asking exactly? That what you're not convinced about?
Actually, it was just because before we were having I0 E. Okay, well, I can't really find it. But the point is the two. Oh yeah, in the source follower we had I0 E to the power of kappa V in minus V out equal to I0 E to the power of kappa VB.
Right.
And I was wondering whether I0 is still the same or it changes for any kind of reason.
Yeah.
We assume that it will be the same actually.
Yeah, usually when you do analysis, you assume it's the same. Of course, you have to assume that all the transistors are equally sized, right? And the it's not exactly the same, right? Because the top transistor of the source follower has a source that's not tied to ground, right? It's actually tied to V out. And then if you know about this back body effect, so if the source of the transistor changes, then it effectively looks like the threshold of the transistor is changing. Right, so let me see if I can go back to that slide to see here still. Yeah, here we go. Yeah, you see between these two transistors, right? You see the source of this guy is tied to ground, and the source of this M1 transistor, this M1 transistor, it's tied to V out, right? It's not tied to source. And so if the source of your NFET is not sitting at ground, that means effectively it looks like the threshold of the transistor has shifted.
Okay.
Yeah, so remember the transistor actually has 4 terminals, right? It's got the drain, source, gate, and bulk.
Okay.
Right, and everything is relative to the source. But if the source here changes, then that means that effectively, even if you put the same gate voltage, right? If I draw, I need to be careful what I'm saying here. So if I do this, right, V gate, and this is ground and this is V out, right? The current that flows through this transistor and the current that flows through this transistor are not the same. But you'll find that there is a difference. Yeah.
Makes sense.
So, but you know,
independent.
Yeah, it does depend on a bunch of stuff, but usually we try to keep things that's more simple for the moment, right? Because then it's easier to solve the equations and get an idea of what that circuit's doing. Yeah.
Perfect. Thank you.
You can make this, you know, like when the circuits can be analyzed to some great level of detail. Yeah, so that's why it makes it interesting also. Okay, so for the differential pair, then if you remember from last time, so I guess I won't derive it again, but you can write I1. You should have it from your notes, right? Also, so I just write it here. So if somebody wants to have it reanalyzed, then let me know. I'll wait for you to mention this in the chat. The question on the diff pair, why are we interested in keeping the common voltage constant? Which common voltage? Are you talking about VS? As we did in the lab. Huh. Okay. That's a yes and a no. More, I don't understand that. Common voltage as V1 times V2 over 2. Oh, yeah. Okay, all right. I have to make so you're talking about actually something different. It's called the common mode voltage. Right. So I'm gonna use common source voltage for VS, and I want to be sure that you don't mix the two up, right? So common mode voltage, right, is V1 plus V2 over 2. Okay, and why do you want to keep it constant? All right, don't really need to keep it constant, but where your common voltage sits affects Vs, right? So this is what we're going to derive now, and you'll see that Vs depends on V1 and V2, exactly where they sit, right? But for the differential pair, when you write the equations, it will look like you don't need to care about it because everything is V1 minus V2 or V2 minus V1, right? So who cares what the actual values of V1 and V2 are? But they do matter, right? And you'll see that in this analysis that I'll show that it does affect how the circuit will behave depending on where you put V1 and V2 at. Okay, is that good? Okay, so now for the current through I1, so that's just E kappa V1, 2, right? And I2 is IB E kappa V2. Right, and then remember you could plot the picture, and then you get this hopefully very nice curves. This is not looking like the exponential it should. Okay, and so one of them will be I1, I2, and then you have the delta V equals to 0 here. And this is IB, right? That's the most current you're ever going to get out of the diff pair. Okay, now the one thing just to show that the reason the circuits are also interesting. Yeah, so let me go back to this thing here. Is that you know the sigmoid function, right? So the sigmoid function says that f of x is equals to 1 over 1 plus e minus alpha x, right? And so you can see from this equation above here, this I1 equation, that I can rewrite this. And so I1, you can divide the top and bottom by e kappa v1. And so then you get exponential of kappa v2 minus v1 over ut. Yeah. So you can see this form here is exactly here. Yeah. So that's why, huh?
The video crashed for a couple of seconds. The video crashed for a couple of seconds, and you were freeze too. So we kind of missed the last few seconds.
Oh, okay. All right. So what is, so I'll just repeat it's for this slide, right?
Yeah, it's for this slide.
Yeah. Okay. So what I was saying is that if you look at the equation for how I1 depends on delta V, right? So this is the equation which we also call Fermi function, right? And then this is the equation for a sigmoid. And so you use the sigmoid function quite a lot in say neural networks when you build an analog neuron. And so then if you say, if I want to build an analog neuron circuit that has a sigmoid transfer function, then you can do this already via this equations here, right? Because if I take I1, this equation here, and I divide the top and the bottom by e kappa v1, then I get this resulting equation here, where I1 is equals to IB over 1 plus e kappa v2 minus v1 over ut. And you can see the form of this equation here is very similar to this equation, right? So if your input, if your x can be defined by a delta v, right? If the x can be defined by a delta v, then you have a very similar equation. right? You can actually do a circuit implementation of a sigmoid. Okay, is that good? Okay, and then now we're going to attach current mirrors at the top and bottom. Going to do this. The out, and then this would be, say, I out, right? I can do I1, I2, IB, and VB. Now, remember what I said before, you can take any circuit and you can flip it, right? So that everything, so you basically replace the NFETs with PFETs and the PFETs with NFETs. Okay, and so if I do now this, this is the transconductance amplifier, by the way. Say it's an N-type transconductance amplifier, but I can flip this thing, and then what would it look like? So again, the NFET becomes PFET, but now it has to go to the top. It's type to VDD, and this is VB, right? And then I can turn this B1 and B2, right? And now my PFET current mirror is going to become an NFET current mirror. Yeah. Okay, and then I have an output, same thing, right? Except now my current is coming from VDD, and then this whole thing, this is still a transconductance amplifier. It's just a P-type transconductance amplifier. Okay, and of course you cannot set VB to, in this case you would set VB to about anywhere from 0.3 to 0.8 volts, right? If you want it to be in subthreshold, and here, remember, it has to be reference to VDD, right? So if this is say a 3.3 volt power supply, then this would be anywhere from say 3 volts to equivalently, so say to 2.6 volts. So you have to set the voltages according to whether your bias transistor is a PFET type bias transistor for this transconductance amplifier, or it's an N-type bias transistor, right? For an N-type transconductance amplifier. Okay, let me erase this. So any questions so far?
Yes,
Mm-hmm.
we can assume that the current goes out on the out, and it doesn't have to necessarily flow from the PFET above to the M2.
Yeah. So this is. It depends on what you hang on top of on V out, right? So it's very possible for current to flow out of this circuit. Yeah. Of course, if it's like open. If you're operating open loop, basically it's just saying that, you don't hang anything on V out, you just measure V out, right? Depending on what V1, V2 changing, then that is true, because the I out that you get in the end is going to change V out so that everything satisfies Kirchhoff current law in steady state.
Okay. Perfect, thanks.
Yeah, sure. Yeah, the circuits are all very interesting, aren't they? Okay, let's see now. What's the other thing that we wanted to go over today? Oh, yes, right. Okay, and again, remember you have this curve, right, of the I out as a function of delta V, and then you're going to get something that goes like this. It should be like a tanh. Okay. Like this. Yeah, and it should look like that. Right. So then this would be IB and minus IB. This is I out. And so you can write I out, which is I1 minus I2, right? And then you can solve this, and this is a tanh of kappa V1 minus V2 over 2 UT. And remember the transconductance GM, which is the change in I out as a function of change in V1 minus V2. So basically we're talking about the slope here, right? How much does I out change for a change in V1 minus V2? And then you can differentiate the equation, and that should give you kappa IV over 2 UT. Okay. And also remember, if you operate this in subthreshold, then you're going to stay with some fixed region over here, right? Remember, because the transistors in subthreshold saturate around 100 millivolts. So which means now if I change IB, right, so that I change IB, but this IB current still ensures that the circuit stays in subthreshold. So let me say I change it to IB2. That one. Then you're going to saturate at similar place, okay? It's like IB2. Okay, so this region over here is approximately about the same. So the only way, of course, is if, some people want to operate this so that you could change the slope of this curve, but not just over this limited range, but also, so basically you want to go further out, right? So say I want to go this much out. And so the way that you would have to do it is to run the circuit above threshold, right? Because that, when you run the circuit above threshold, then this region will grow depending on where you set the bias voltage of the transistor. Okay. And so you'll see maybe in a little bit that you can actually use this as some sort of a resistor, right? Because you do have something here where the current changes as a function of the voltage, right? So you can operate a bit like a resistor, but if you want to be able to change this conductance here, right, this GM, then you'll see that people run it above threshold. Like if you look at the circuits for the group in Heidelberg that builds the above threshold transistor circuits, or they use above threshold transistor circuits to implement neutron circuits, and partially it's because they want to have this linearity for a much bigger range of delta V's, right? But then the price that you pay is that the circuits will burn more current. So these are some of the trade-offs that we have to think about, right? Because if you run circuits sub-threshold, it burns less current, but you're also limited to certain things that you can do. I mean, especially if the exponentials, they're just wonderful. But if you want to insist on having linearity over a much bigger range, then you have to run them above threshold and you're going to burn more current. Yeah, okay, so Adrian, you have a question? You're asking about Vmin already, man. And Hector has a question. Is there a connection above the transistor with V1, or is the cable passing over? Okay, sorry, I didn't see this before. So Hector, did you get your answer? Oh, it's diode connected. Okay. Oh, yeah. Do feel free to help those who ask questions. Oh, are you asking this one here? Yeah, this is diode connected. Is that what you're asking? I guess so. All right. Yes. Yeah. Okay. So now let's talk about this. This common source is going to be interesting. Okay. So we're going to derive the common source voltage. Right. Let me start again. You're going to ask me whether okay, this is diode connected. It's a PFET mirror. So I just yes. And then I'm going to give this guy's name. It's also in the PowerPoint. So you guys have the PowerPoint and you can see this. Let me see where you guys are at in your PowerPoint. So if you go to slide, yeah, so I skip over the slides where you have to compute the GM for above threshold. Okay, so I'll leave that to you guys. Here, so on slide 16, right, for those of you who are following the slides. Sorry, I'm trying to get back to my window. Okay, here we go. All right. So for the analysis that I did before, we assume that all the transistors are in saturation. I'm just going to also go ahead and label these transistors with this name. This is M5, M4, M1, M2, and M3. Okay. So now, can you assume that they're in saturation all the time? Right, so we can't, because it really depends on where these voltages are sitting, right? So it's good to assume they're in saturation initially because you just want to get an idea of how the circuit works. And then you see what happens when they don't really sit at the place that you hope they would sit at, okay? So the first thing you do is that you want to set the bias transistor equation so that it's not in saturation. So here's IB, right? And so what you would write now is, instead of saying that IB equals to I naught E capital BB, we're going to say that IB is equals to, I'm going to drop the UT because equations tend to get a bit ugly, okay? But just remember there is UT at the bottom. Okay, so this is the equation of the current flowing through the bias transistor when you don't assume that they're in saturation. Okay, so the first thing is you assume that these two transistors are operating in saturation. Okay, so that means you can still use the same KCL equation. It does not matter whether they are in saturation or not, but you can always use the Kirchhoff's current law equation, Kirchhoff's current law. Okay, and so what you do then is you say I naught. It's just that equations gonna get a bit more interesting. Okay, so then this is for IB, and then you can write again, we assume that all the I naughts are the same just to make things simpler, right, for the analysis. Okay, then what you can do then is to try and solve this equation for E minus Vs. And of course you can, if you assume I naughts are the same, then you can cancel all these guys out. And then if you rearrange the terms, then what you get is, it's on the slide. So it's E minus Vs, okay. You can put UT if you like. Okay, so then you get E capital BB. Okay, let me put the UT. So it's the same as what you see there. So okay, so it's not very pretty, but not too bad, right? So basically it's exponential of the bias voltage and then divided by the exponentials of the three voltages that you can control. Okay, now so the circuit shouldn't operate too differently if you can ensure that this transistor stays in saturation. And for this transistor to stay in saturation, you know that the drain voltage, which is Vs in this case, we call it Vs, has to be greater than 4 UT, right? Because otherwise you'll go out of saturation. And if it goes out of saturation, then the bias current that you have is not the one that you get when this transistor is in saturation. Okay, and so which means that if you want Vs to be greater than minus 4 ut, this exponential term over here will be greater than 1, right? It's much greater than 1. Okay, so which means now you have still this equation here, but you know that this equation has to be, this equation here has to be much greater than 1. And so what you can do then is you take this away, right? So I'm going to take this part away. I'm going to say that this is much greater than 1, right? And now I'm going to take this term, the denominator, I'm going to put it over to the other side. And so I'm going to erase this guys here. Right. And so what you're going to end up with is, E kappa BB over UT is, see, this is correct. Okay, is that good? Just make sure we don't find any, I think this is, actually guys, this is, I think this is the other way. Okay, okay. Well, I can't push this thing to the side, but you know what I mean, right? It's good. Okay, it's good. All right, so that means that now you can redo this, right? So you know that V1 and V2 are both greater than VB, right? So that means you can assume that these two terms are going to dominate this term. So then what you can do is you can rewrite this again and you say E kappa V1 over UT plus E kappa V2 over UT kappa V. So that's where you get equation 2. Is everybody okay with that? Oh, I see there's a equation, there's a question. The analysis we're doing now seems to be large signal swings of V1 minus V2 and V2. Yeah, so here this for this equations I'm solving, I'm not bringing GM in, right? So it's not small signal, you're right. So you don't have to use GM for this analysis. Is that good, Chaim?
Yeah, it was actually for the previous one when you were analyzing.
Oh, I see. Okay. All right. Yeah, that was really for, I mean, you're right. It's for small signal. So it's saying that whenever there's a small change in delta V, then how much does the current change? Yeah. So then you can talk about GM, but for large signal, you cannot talk about GM.
Yeah. So the one which we were analyzing before when you were plotting the V1 going from all the extremes. So that was a large signal analysis, right?
Yeah, except for that region. Let me go back to it. Let me find my mouse. Yeah, you're talking about, see, which one was it? This one here, maybe?
No.
Oh, no, not this one. I know which one you're talking about, this one.
Yes.
Yeah, right. I'm talking about here, this
Okay.
part. Yeah, then it's okay. But you're right, out here, you cannot use GM.
Okay.
Yeah.
Yeah. Thanks.
Okay, so then going back to this, so now you have one equation, so that's equation 2 on the slides, right? And then what you need to do now is you have to put this back into, this is really tough, right? So you have to take this equation, like, so you can see from the slide, right? So you take this equation and you put back okay, how should I do this so it doesn't look so messy? I'm gonna rewrite this. Erase this. And we go back to our original equation, which says how get rid of this. Okay, so you go back to this equation, right? And then what you can do is first with this equation, you take the log on both sides, okay? And so if you take the log on both sides, then you have minus Vs. That's how you get to the other one. Minus Vs over Ut equals to kappa Vb over Ut minus, yeah, this is the ugly one, which is the log, right? Minus the log of E kappa Vb over Ut plus dot 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 plus this other two terms. So you guys know how we get the Vs, yeah? And then you can make this positive, right? So again, then it will look like this, okay? And then drop the U, I mean, not drop the UT, multiply each of the terms by UT, and then what you get, let me turn to red here, is Vs will be equals to minus kappa Vb, and you have to multiply this by UT, and it's log of this set of terms over here. Yeah, is that good? And then remember, we have this equation here at the top, this equation. And if you use this equation, then you're saying that this two terms, the exponential of kb1 and kb2 dominates this one, right? So that means that you can throw out one of the three terms, and then you can simplify the whole thing, right? Because then now, let me see if this fits in here, right? So this would be log of E kappa V1 over UT plus E kappa V2 over UT. Yeah, it's a bit tricky. Okay. And then you can simplify, if you assume that V1 and V2 are greater than this 4 UT, then you can simplify it. So basically, in the end, it's saying that one of the two terms over here, one of these two terms will dominate, right? So either it's the V1, if V1 is much greater than V2, or V2 is much greater than V1, okay? And so then you're left with this, this equation. So let me delete this now. So it shows you how the common source voltage depends on V1, V2, and VB, depending, and also dependent on how much V1 is greater than V2. Okay. So if you go through this, then you will see that Vs is equals to the max, right? Times the max of V1, V2 minus VB. Can you guys see this? Because, okay, so I think, all right, let me do one more step before I get to this final equation, because I think it's too difficult to see it. Okay, so this is minus kappa VB plus UT log of E kappa V1 over UT, right? Yeah. Plus E kappa V2. And so now what I can do is say, I can say V1 is greater than V2 by 4 UT. Then the corresponding equation would be Vs equals to minus V plus UT log of E kappa V1 over UT. So basically, I'm just going to assume now that this E kappa V1 or E kappa V2 over UT term is much smaller than E kappa V1 over UT. Okay, and so then you're left with this equation. And so that means now if I rewrite it, it would be UT kappa V1 over UT. Right? So taking the log of the exponential. Then I can cancel this, and that gives me minus capital VB plus capital V1. Do you guys see that? Oh, why did we neglect it? It's because when, remember when I solved for E capital VB, when I make the assumption that I want the bias transistor here to be in saturation, I have to assume that Vs has to be greater than 4 UT. And then we went through the analysis, and then we found that in green here, this, or in, yeah, in green here, this equation.
Yes, but
So that means you can, so the idea is to just keep on simplifying, because you have 3 exponential terms, right? They're added together. So it's a bit ugly to try and do a log of 3 exponential terms. So you try to figure out which term is dominating, depending on the conditions.
yes,
Right.
but in the nominator, in this case, wasn't there also a term which was E plus kappa, E to the power of kappa, VB over UT?
UT, yeah. So basically I threw out that term because E capital V1 over UT has to be bigger than E capital VB over UT, because V1 is greater than VB, right? For to operate the diff pair, the V1 and V2 have to be bigger than VB.
Okay.
Right? I mean, they have to, because otherwise the VS will, okay, so let me try and show you this. Right, so if I make, do you want me to show you? Wait. So remember this, oh boy. So the current through this bias transistor here is IB, right? So which means that the current that can flow through here is IB. Okay, IB over 2, if you make them both the same, is IB over 2 on both sides, right? But let's assume that I make V1 much greater than V2, right? Then the current that flows through this transistor is IB, right? Let me try IB, yeah, you agree?
Yes, yes.
Okay, which means that, remember the current depends on VGS, right? Gate to source voltage. And what is the gate to source voltage of this transistor?
At most VB should be.
Yeah, it must be VB, right?
Okay.
And if V1 is set to VB, then VS, where is it going to go? It can't go anywhere that's high, and you know what I mean?
Okay.
Right?
Okay,
Yeah.
so fixed in this case.
Right, so that's why V1 has to be greater than VB for the whole thing to work, and then E capital V1 must be bigger than E capital VB. And so then you just kind of simplify and start dropping terms. Yeah.
Okay.
Okay.
Thanks.
All right. Sure. Oh, again, that was because Mar has this question. It's because of this assumption that we make here, that with this transistor, the bias transistor has to operate in a saturation, which means that you know that Vs, I shouldn't call it Vs, but anyway, it's too late. All your notes call this Vs, right? It's because Vs has to be greater than 4 UT. So the exponential of this, you know, it's going to be much smaller than 1. Okay, all right. So that means that you're left with a very nice simple equation with all the dropping of the terms. And so you end up with what you see here on slide 20. Yeah, it says that the source is kappa times the maximum of V1 or V2, whichever one is bigger, minus VB, right? And the saturation condition for M3, which is the bias transistor, right, where you have to ensure that Vs is greater than 4 UT, is that the maximum of V1 or V2 has to be VB. Yeah, so that's what we were just discussing, right? It has to be the bias voltage plus 4 UT over kappa, right? So that's the sort of where you have to set V1 and V2, right? So it has to be at least VB, the bias voltage, plus 4 UT over kappa, right? So a few more 100 millivolts, okay? And if you don't have this this condition satisfied. So that's why this common mode voltage is important. You know, when we were talking about the common mode input voltage, right, which is voltage, which is equals to terrible handwriting right now, V1 plus V2 over 2, right? So if this common mode voltage is not put in the proper place, then this transistor is not in saturation, and then your transconductance amplifier circuit won't work well. Okay. That's why it's important to know where it is. Okay, everything good? So now we go to the output transistors. Okay. Let's see now. Let's make another slide in case we need to go back to it. It's funny how a 5 transistor circuit can lead to so much analysis. So you have VB, V source, V1, V2. Okay, so now we have to talk about the output transistors. So in this case, let me give the names that are in the thing. This is M5, this is M4, or what is it? M2, sorry, M2, 3, M4. Okay, so we also made the assumption when we were deriving the Tench function was that these two transistors are in saturation. So this should be in saturation because it's direct connected, but we didn't say anything about whether this should stay in saturation all the way, M5, or even this should stay in saturation all the way, right, M2. And so this are your output transistors there, or the transistors that are tied to the output node. So we call them the output transistors, so M5 and M2. Okay. So you can see to keep M5 in saturation, you need to guarantee, right? Because this is again the VDS here, right? It's going to be VDD minus V out, right? And that has to be greater than 4 UT. So that's for M5. And then if you want to keep M2 in saturation, right, it's the same thing. Again, you look at the VDS, DS here. It's going to be ugly again. Okay, VDS here. Yeah. And remember, this is an NFET. M2 is an NFET, M5 is a PFET, right? So that means this out minus VS has to be greater than 4 UT. Okay. All right. So that means, let's see now. What do we have from before now? 1 second. Need that one equation. Okay, so if V out, so we know that VS, like from before the previous slide, Vx has to be the max of V1 to minus VB. Okay, that means for M2 to stay in saturation, so V out minus Vs has to be greater than 4 UT. Let me see if I can get to that. So V out has to be great. So we have to move Vs to the other side. So V out has to be greater than kappa max of V1, V2 minus VB for UT. You guys see that? Okay. So that tells you something, that for the transistors to stay in saturation, the V out has to be greater than some value, right? And so we actually call this the V min problem, right? V min problem. Because it's saying that this is the minimum voltage that V out can go to. So it can never go down to ground, right? So if I want to use this transconductance amplifier circuit, let me use my cursor here. Yeah, can you see my cursor? So if I want to use this transconductance amplifier circuit, say like a voltage amplifier, right? Where I have V1, V2, and then V out, then I'm not going to get V out to go to ground, right? You can go close to VDD. In fact, for it to stay in saturation, you just have to ensure that V out doesn't drop from, doesn't approach VDD by at least 4 UT. Well, you have to be away from VDD by at least 4 UT. But V out cannot go all the way to ground, right? It has to be greater than this value. So do you guys get the V min problem now? Are you guys a bit lost why we did this analysis? Okay, no one's answering. Yes, makes sense? Okay, if it doesn't make sense, you should say. So it's just kind of something that, yeah, you should appreciate, at least because if you're going to use the circuits, you have to understand why you would see, say, for example, that V out cannot drop below ground, why, you know, especially if you're going to use the circuit, for example, to drive yet another circuit. So if V out becomes the V in of yet another circuit, and you're assuming that that V in can move all the way to ground, right? Then you're going to be surprised, right? Because here it's saying that V out will never go close to ground. Right, so you cannot assume that if I want an input voltage that goes all the way from VDD to ground, I'm going to get it out of this circuit, because you won't, right? So you might want to change that circuit if that's what you're looking for. And last week we analyzed this wide range transconductance amplifier where the V out can actually move all the way from VDD to ground. Okay, and then you should swap in the proper circuit. All right. And so now you can combine both things together, both conditions together. And I guess I can write it, or I won't write it. No. Oh, yeah, I can write it. Actually, let me do that. Okay, so this would be VDD minus 4 UT, okay, on this side. And so this is your constraint of the, if you, for the two transistors to stay in saturation. And then if you look at the slides, if you measure, if you set V1 equals to V2, and then you measure how I out changes as a function of V out, right? You're going to see a curve that looks like this if you actually do measurements. So let me draw this again, because it's always helpful to have the circuit next to you. And so here you're going to set, you can set V1 equals to V2. And then what you do here is if you attach some, say, voltage source to the output, and then I'm going to move this output, right? So this is what I'm doing here. I'm actually moving my output in this curve that I'm showing. It goes between, say, 1 volt to 5 volts. So this is quite an older process where VDD is 5 volts. So if I attach a power supply here, right? And then now I basically change the output voltage on this power supply, right? I say, what would happen to the current that's coming out of here, right? And this is I out. And remember, I out is equals to I1 minus I2. Right? So now if I measure I out, I find that it's not constant, right? So first you would think that if I move the output voltage around, I hope that I out just stays where it is, right? So basically I would like it to be like this. That would be nice. And in fact, you can think of this I out versus V out curve over here. Right, this is like the output conductance of the transconductance amplifier. Like, so you don't have it as infinity, right? Ideally, you want the GD to be infinity, like to zero, sorry, to be zero. But actually, you do get this also this finite conductance. And so the question is why that happens. Well, that happens because of the conditions that we saw about the current, because the current that flows through each of these nodes here, let me just pick a color. The current that flows through, do red. So the current that flows through here and that flows through here, right, depends on where this voltage sits at, right? So you do affect the current flowing through these transistors. And because of that, the output current flowing out also changes, right? So it's not, so in other words, I'm saying it's not I1 minus I2, right? But rather it's some I1 plus delta I1, and that would depend on where the V out sits, minus I2 plus delta I2. And that's why you get this changing output current as a function of the output voltage. Yeah, and you can see that also when the output voltage increases towards VDD, which is saying that this V out approaches VDD, then you can see the current drops by a lot, right? Because now this transistor here is going out of saturation, right? And so that's why the current drops. And then you get this interesting part over here, which is the Vmin problem, right, that we talked about. And you can see on the curve, it's actually around 1 volt in this case. And so now it looks like the output current actually is increasing, right? But it's increasing in the opposite direction. And so that happens because if I start dropping V out more and more, right, at some point, so this is Vs here, right? So if V out becomes less than Vs, right, then what happens to the current that flows through this transistor? Is the current still flowing in this direction? Oh, I1 and I2, yeah, I always assume I1 and I2. So Hector has a question. I1 and I2 for me is always the current going through here. It's always like the, you know, the diff pair current. Right, and I can say IR equals to I1 minus I2 because I assume that the current that flows through this PFET is I1, right? There's only one way for the current to flow. And then if this current mirror is perfect, then the current that flows to here is also I1. So I will, let me do this again, so that you understand this. Take all this away. This pen is tricky, man. Okay, when I say I1, I2, I always mean it's the current flowing through these two transistors, right? So V1, V2, and this is I2 and I1. Okay, is that good, Hector? And then the current through this PFET, let me finish drawing the circuit again. Cool. Okay, not drawing up to my VL here. This is VL, right? So the current flowing through this transistor, let me label green, this current here, right, should be equals to I1, right? And the reason for that is because there's only one way for the current to come through, and it's through here. Yeah, okay, Nicola has a question. This configuration, we can't have V2 greater than V1, right? No, we can. Nothing wrong with that. Why would you? Okay, I mean, no, you can set V1 greater than V2 or vice versa. You can change the voltages. I mean, of course, the VI will sit in a different place, that's all. Okay, so I1 to the PFET mirror is mirrored back out here as I1, and then here's I2, and so I out, right, should be I1 minus I2. Okay. All right, so when the V out is less than VS here, right, then what happens is the current, instead of going this way, actually goes the other way. I should make it red. Actually goes this way, because now for this transistor, this is now the source, right? Remember, the drain and source are interchangeable. It depends on which node has the higher voltage, right? If V out is less than VS, then current actually goes out that way. It's a bit weird. So do you guys understand that? And that's why you see this huge current. Right? It's because the current now is flowing the other way. Oh yeah, okay, Nicola, your question. Yes, if you make V1 greater than V2, sorry, V2 greater than V1, then I2 is greater than I1. And so then, you know, the voltages will also in the place that in the end, this currents will all balance out. So it wouldn't be like the I2 and I1 corresponding to all these transistors staying in saturation, right? Because you notice that, you know, when VS is not at the place where it should be, then this IB current will move, right? It's no longer at the saturation IB current, right? In fact, it could go very close to a small current, much smaller than IB. So you can think of this now as like IB prime or something, right? And the same thing here, when you make V2 greater than V1, then I2 flows to here, but then I2, the net current, okay, this is probably going to be ugly to see till I redraw everything. Just remember Kirchhoff's current law applies for steady state. So everything will move to where it needs to, so that the circuit voltages won't change anymore, but it wouldn't be, you know, the transfer function that you're hoping to get, right? So like the transfer function is something that you get only if all the transistors operate in saturation, right? So that means that even if, let me draw a second here. So even if this transistor goes out of saturation, then you don't longer get like this nice tension function anymore, right? You got it, Nicola? I mean, I can do whatever I want to the circuit, right? It's just that the V out will sit in some place so that I can be guaranteed that all the currents here are going to match up, right? It wouldn't be I2, the I2 that you would get if everything was in saturation. It would be some current, yeah. And then the same for here, because the only way that the voltages will not move anymore is that when the current coming in to that node minus the current going out of that node is equals to 0. Yeah. Oh yeah, well, right. So this is the weird thing there. Yeah, so if you hang, like, you know, if I drive this output voltage, if I make this output voltage smaller than Vs, so if V out is less than Vs, then basically this is the source of the transistor for what is this one again? M2, right? So we're talking only about this transistor here. Right, so this is now becomes the source and this becomes the drain, right? And so that means that effectively you kind of see a current that's actually going out this way. Yeah, it's a bit weird. The only reason why you can see this change in output current is because the current actually comes from a voltage source that you apply, right? Like the one you use in your lab, right? If you don't have something that can provide that current, then the voltage will move someplace, right? You'll never get V out going below Vs. So you don't have to worry about that, right? Okay, so transistor's not in breakdown. Okay, all right. Any other questions? Okay, so now let's go to the voltage amplifier. Back to the good old transconductance amplifier. Okay, so what if I want to operate this as a amplifier, a voltage amplifier circuit? So remember, for an amplifier, you have a plus and a minus, right? And then you have an output. In this case, it's easy because it's V out, right? So now the question is, well, is V1 the plus? Who is the plus here? Is it V1 or V2? Or is it V1 or V2 here, right? So for you to be the plus node, then remember the current, the equation for a voltage amplifier is V out is equals to the gain, V plus minus the V minus, right? And so that means, let's see what happens. If you can't, you can reason through it, right? So let's look at the circuit here on the left and say this one goes up, right? So V1 is greater than V2. So let me use the mouse here so I can show you with the mouse. Okay, so V1 is greater than V2, which means all the current flows through here, right? So let me do IB also. So IB flows through here, and that means IB flows through here. It gets mirrored here, which means that now IB is charging V out, right? So you can always think there's a little capacitor here. So V out will increase, okay? So if now we do the opposite, let's see what happens. So we would assume that this is V1, right? It's a plus node. Let's assume now that V2 goes up. So what would happen? So V2 goes up, current now increases through here, or it flows through here instead of through here. And now you have a current that's discharging V out, right? So that means this output voltage would drop, right? For V2 increasing, V out drops. What is, Nicola, I don't understand your question here. Okay, so
no, it wasn't a question. It was just to say that V1 was at the plus end. I wanted to ask if it was correct. Just that.
Oh, I see. Okay, all right. I thought you mean plus something. Okay, all right. That's correct. Yeah. So there we go. So you have V1, V2, and V out. Yeah, so you know, it's sometimes good to be able to reason through it, especially if I now take my transconductance amplifier and I flip it around and I ask you whether V1 is still the plus terminal, right? It's a good question. So you could do that for your exercise for next time. Okay, so now since you know that it's some, you can write the this differential input voltage amplifier circuit that you see here through this equation, right? So now the question is, what is this A, right? And this A, remember from it's delta V out over delta V in, right? And then we can write this as V out over delta I times delta I over delta V in, right? And this is a GD, right? Drain conductance. And, oh, sorry, actually, this is wrong. It's one over GD, right? Times GM. You guys see that? Yeah? Yes? Okay, so that means that in subthreshold, you already know what it is, right? You guys know for subthreshold, GM is kappa I over UT, or actually kappa I over 2 UT. And then GD is the drain conductance of both these transistors. Okay. And so you can essentially write it as then kappa VE over 2 UT. Okay, any questions? No? All right. Yes? All right. Okay, then you can do the same if you want to compute what the gain would be for when it's doing above threshold. Okay, so the next thing is this circuit actually good to be used as a voltage amplifier? well, actually, if you go through and compute this A here, right, given that you know what the early voltage is and also UT, you can actually get values between 100 to 1,000, right? So it's actually not bad, right? It's actually pretty good values, right? And then you know that you can increase the gain of the transistor by making sure that the early voltage is large. And you guys already know how to make the early voltage large, right? It's by making the length long. Right, so this two transistors, that's what you care about, right? So you want to make those long, but of course, if you want to match the mirrors, then this also has to be long. And same thing here, right? This would have to match this one. Okay. So you can make a high gain, if you like, a high gain voltage amplifier, but usually we don't use this as a voltage amplifier, right? We actually use this in a different configuration. Usually it's in some sort of a feedback loop, right? So you could put a resistor here. You could actually even do this. You don't even have to put any element. You can tie the negative terminal back to the output, right? So this is what they call a negative feedback configuration. Any questions about that? So you guys know what negative and positive feedback is, right? Why would we want to have a higher early voltage? Because your gain A depends on the early voltage. Right? So A is capital VE over 2 UT. So the higher you make VE, the higher the gain would be. You always want to have a high gain amplifier. So that way you're very sensitive to small changes in the voltage. So as soon as the delta V changes by some amount, right, then this output will move a lot. Okay. Okay, so this is kind of what we call operating in the open voltage mode, right? You don't have any feedback. Open loop, yeah. And so this we do use in neuromorphic circuits, but the way we use it is as a voltage comparator. So for example, if you're building a neuron circuit and this would then be like the threshold of the neuron, right? And so this would be, say, the memory potential of your neuron. And so the memory potential might start moving up, up, up because there's current coming in. So say it's going up like this over time. Right, then as soon as it crosses the threshold, so right, so let me put this as the voltage, right? So this would be your VTH, if you like. So when you cross the threshold, then you want the output to really go up. Okay, so I have to pick a different color. Right, so this is out. Right, so then the output will go like this. Okay, so that's like producing a spike then. And so people do use this the circuit here as a voltage amplifier, a comparator. Right. Questions? No. Okay, so this next part also here is a bit tricky. It's a little bit like the V-min problem, and let's see now. So you guys see the slides? Yes, I tried to put it again in some set of equations. So this is what happens when you operate it as a voltage amplifier circuit. So maybe let's just look at the curves first. Right, so if you go to slide 28, right? So you see this curve over here where you have V1 voltage, and then you're sweeping here from say 0 to 5 volts. This is for an older process. That's why it goes all the way to 5. Yeah. And then here's your V out. Right, then you're going to set V2 to different voltages. So in the first one, you see that you set V2 to 0.5 volts, right? So V2 equals to 0.5 volts. And I'm going to sweep V1. And what you get when you look at how V out changes, well, it looks like this, right? You can see there. And very quickly it goes to V out. It goes to VDD. right? So you can see it's got very high gain here, right? So when V1 becomes greater than V2, then boom, it goes to VDD, right? But then the interesting bit is that when you start increasing, so let me take a different color for this next thing here. So here I'm going to set V2 equals to 1 volt. And here you hope that it would go like this, right? So this will maybe be at 1 volt. Then I go boom. Ah, man. Right. I quickly jump to here. But it turns out you don't actually. If you look at the set of curves here, right, you see there's this thing here, and then it kind of slews up, right? And then it hits this high gain region, and then it slams all the way to VDD. Right, and then I could take the next one and say, let's do V2 equals to 1.5 volts, right? And then what happens is you go like this, and then at some point you start going up, right? And then you can see it goes straight up, and then this, right? And so on. So if I have now another voltage, then yeah, you see this set of curves that go like this. So the output, as you can see, can never drop below. You cannot get this high gain region till you reach some value, right? So this is what you can compute. You can analyze why this is the case. Why do I not, get what we prefer is a curve that would be like this, right? And the red one would be like this, and then the blue one would be like this, and so on. Yeah, it's kind of a mystery. And so this you can actually analyze by, again, looking at the very similar equations to what you've already seen before, right? So are you guys all looking at the slides? Because then I can just do it from there. Otherwise, what I can do is, let me do the power. Okay, so for the output voltage, you have to compute the limits of the voltage swing, right? So you have the first case here. So when V1 is greater than V2, right, then if V1 is much greater than V2 by 4 UT, then the current that flows through M2 is much smaller than M1, right? So which means that Vout will go almost to VDD to shut off M5. So remember what I said is you can set the voltages to anything you want, but in the end, the Kirchhoff's current law is going to apply, right? So in this case here, because I2 will be very small, then this current flowing to M5 has to be also very small. Yeah. So which means that M5 has to be out of saturation, right? Means the V out has to be less than VDD minus V out has to be less than 4 UT. Yeah, you guys get that? There's always this balance that's going on, right? And if the output voltage has to move in some way to make the currents balance out, right? Then something's going to happen to where the transistors are operating. Right? So in this case, M5 goes out of saturation. And the same thing for when V2 is greater than V1. Oh, I have to fix this on the slides. Somehow it shows up as a funny thing. So again, when V2 is greater than V1, then you're going to get a huge current over here, right, for I2, right? But then you know that the top current has to be equals to the bottom current, right? The current for M5 has to be the same as the current for M2. And so in that case, again, something is going to happen to V out so that you're going to get this balance. Right? So which means that you don't really get I2 as IB, but it's going to be a lot less than IB also. Right? Is that clear? Okay. No, nothing. Okay. So for proper operation, you want to ensure that the output transistors M2 and M5 are in saturation. And so now you just make a simple assumption that V1 is a little bit greater than V2, not too much. And then V out will be somewhere close to Vs, right? Actually, I think this is a mistake. Actually, it's V2 greater than V1. Yeah, so I have to fix this also. So then you could take this equation over here, like before, right? We solved this in the previous slides. And then, sorry. In this case, what you do is, again, you assume that V1 and V2 are approximately the same. Then you're going to sum them together. And so that's when you get this equation E cap of VB or E cap of VB plus 2, E cap of V1 over UT. And then you divide the top and bottom by 2, factor of 2, then you get a half on the top and bottom here. And you no longer have the factor of 2 here for this term. It's a bit tricky. Okay, now you can actually go through and then place some constraints on V1. So this is a bit ugly, and I'll try and put some more notes in between so that you can see where this comes from. Okay. But if V1 drops below VB by some amount, then basically V out will go to close to ground, which in this case, will never happen, right? And if V1 is greater than this constraint, then you can see that V out is kappa. Again, this is a mistake here. This is V1 minus VB plus UT log of T. So this equation tells you that the output increases linearly with V1 with a slope of kappa, which is what you see here in the slides. You see here? So there is a place where, because of the of where V1 is sitting, because in this curve over here, you're changing V1, right? And so once V1 is greater than this constraint, then the output voltage will increase in this linear manner, where kappa is, where V out increases linearly with the slope of kappa. It's very difficult sometimes to to think about this stuff, right? But it comes because V out, for V out to stay in a certain place, you have to guarantee that all these transistors are in saturation, right? But that doesn't always happen. So as soon as one of the transistors go out of saturation, then another equation comes into play. And this equation is the one then that will give this kind of curves that you see here, right? Where you don't have this kind of high gain region from very early on, but rather you get this kind of slow increase in V out. Then at some point, V1, when it gets much greater than V2 in this case, then you go into the high gain region, right? So I'm not explaining this very well because it's something that really needs some thought, and it's not easy to get it from the equations, but it's a bit sort of understanding that the transistors need to be in saturation for you to get kind of this ideal curves that we were used to expecting. And this is not possible all the time because it depends on where you put V1, V2, VB, and also V out itself, right? Whether you actually tying V out back to the V minus, or whether you're running the transconductance amplifier open loop, right? And then what you see then are kind of this differences that if you go through the equations and you write down, what you think, which transistors are out of saturation, and then you solve the equations again, then you would get the curves that you see, that you measure, right? Because what you measure is real. And also it's the kind of curves you get when Kirchhoff's current law is satisfied, because these are steady state responses. So does that help you? For the moment, I think it's something that you have to think about for sure. I remember when I first saw these curves, it took me, I think, at least a couple of weeks, even maybe more than that, to appreciate. Slowly you appreciate why these things are happening, but it really takes some thought as to why they should happen in the first place. Yeah, what's the slope here? Yeah, it's kappa. I mean, what this is saying is that you cannot run it like a voltage comparator, right? Just kind of imagine that you could run V1 from 0 to 5 volts and expect that you're going to get a nice comparator like you would have, if you have an ideal amplifier circuit like this, right? That because of the configuration of this transistors in the amplifier, you're going to get some differences that you might not expect, right? And if you analyze the equations, then you would understand why it's behaving like this. Yeah, it's somewhat, so here you can see, if I take V2 equals to 1 volt, you can see at V1 equals to 1 volt, it starts changing with this high gain that we expect, right? And the same thing here for V2. It's only when you're sitting at 1.5 volts. So this one, V2 is 1.5 volts, and you see when V1 is 1.5 volts, then you start changing with this high gain that you expect. Yeah, so around here, it's saying that even though V1 is less than V2, right? VR is already changing because of V1, because V1 is actually forcing the currents to be different, right? So that you don't, even though you, okay, what I'm saying is that even though V1 is less than V2 at this, can you see my cursor? At this point over here, this range of values, right? It's actually affecting V1 because of V out, because one of the transistors is going out of saturation. Yeah, so it is related to VB. Yeah, it's correct. That's correct. Yeah. Okay, so, okay. All right, so you guys get the feeling for even with a 5 transconductance amplifier, and you can have the equivalent symbol with the plus and the minus and the output, that you shouldn't assume that it operates exactly like the symbol, right? Because this is kind of an ideal picture where you want the output to change as the function of the difference between the two inputs, right? And depending on the circuit, you might get this to be true for a certain set of conditions, right? A range of values for V1 and V2. And it's also understanding where that is, right? That if you want to design, if you want to be a designer later on and you want to use the 5 transistor transconductance amplifier, you don't make kind of assumptions that you should follow this equation all the time. Yeah. Okay. I think that was it. I think I won't go over this wide range transconductance amplifier circuit because you guys, we did that last time. Did you guys understand this, or you want me to go over it again? Okay, so here we go. Transconductance amplifier. Nice thing is cheap, only 5 transistors, and it's simple. Bad thing, the output voltage is restricted, and also the voltage gain is limited. If you want to have like the widest swing on your V out, then you do a wide output range transconductance amplifier, where instead of having a current mirror on the 2 branches here, you have 2 current mirrors, and then you mirror one of the currents, like I2 here, you mirror it so that it's now the current sink, and so that way you can always do I1 minus I2, right? But this output here can swing all the way from close to VDD and close to ground, right? It doesn't, you can see it's only a single transistor. It's not like this one. See this one, there are 2 transistors in series, right? But this one only has 1. Okay, so good thing output voltage range is unrestricted. The gain can be made larger because you can just increase the length only on these output transistors. You couldn't do it here because you always want to have things match, right? So if I make the length of this transistor big, this transistor has to be big also. And the same thing here. If I want the length here to be big, this one has to be big also. But with here, you're a little bit more independent, right, of what happens here. So you can get a much higher gain. And also the bad thing, of course, is that now you're using an extra 4 transistors, right? So now you have 10 transistors, right? And with analog circuits, one thing that we always have to think about is mismatch, right? So which means that even in a PFET current mirror, if you assume that this transistor, if I make 2 copies of the, say this mirror, I make everything exactly alike, same width and length, put them close together, everything, you'll still find that there is some slight differences in threshold voltage that comes from the fabrication. And so for the same gate voltage, you'll find that the current through these 2 exact copies of this transistor will still be slightly different, right? And this is what we call mismatch, right? Because everything in analog design, right, the output changes for any change in the input voltage or current. Okay, what is the last question here? Does this basically isolate V out from the circuit? Yeah, that's correct. It isolates it from what's going on here in the middle. Okay. And then you can actually go into, the textbooks that people have for analog integrated circuits, and you can see that the amplifier circuits are actually more complicated than this one's here, right? But then they're trying to also, they have different specifications on what the circuit should do. Okay. Yeah, it's related to Vmin. Yeah, that's correct. That's correct, Hector. Okay, great. Yeah, that's guys. I'm glad you're learning a lot. Yeah, it's actually kind of nice to think about even simple circuits. And so next week, we're going to talk about linear systems. So that means we're going to look at how the signals change as a function of time whenever you change one of the input voltages. Right now, everything's kept constant, but what you want to see is, well, if I change V1, all of a sudden, like a step function, maybe, for example, then how does the output voltage change as a function of time, right? And that's also always interesting because, it's going to be dependent on, again, the current to the bias transistor. You probably will have to hang a capacitor here, right? So you can talk about filters, first order filters, second order filters, and so on. Okay. And that's something we use for many different things, like for the cochlear, which is a set of bandpass filters, right? And so, so some of the circuits that you learn will come in useful if you want to design stuff like that later on. Okay, if that's it, if no other questions, then thanks guys for joining and see you next week.